this lesson. So in this lesson, we'll be looking at chapter 6 of this multi-agent orchestration pattern for enterprise scale system. So the content of chapter 6 is scalability and performance for multi-agent system. So architecting for the leap from elegant prototype to high throughput enterprise production system. And in chapter 6, what we discussed there are very, very important, very, very important. So it mimics the microservice architecture of enterprise application where you use a cloud native design pattern or Kubernetes for auto scaling. So we know that this is the season of Kubernetes. Okay, Kubernetes will be the platform, the best platform for deploying multi-agent system because you have pod. You deploy each agent put to a particular pod, and then you have separation of concern, and then you can know which agent is not performing well, what to scale. Do you need to scale? Do you need to scale up or scale down? Do you need to increase the LLM token, or do you need to limit it, and so on and so forth? It helps you determine what needs scaling, so that where you need to increase LLM API call, you are not adding extra agents. So you should know when scaling is needed and what to scale. So this is very, very important for performance engineering in multi-agent system design. So in chapter 6, so we have scalability and performance engineering. So enterprise agent systems must scale beyond demos and small workload. So stateless agents are easier to scale and restart because we know that stateful data should be stored in external systems like Redis, PostgreSQL vector database. We're going to see this in architecture. We talked about all this. Sharding help distribute large workload across agent pools. You will also see this in the architecture. Then we have Kubernetes can run agent as cloud native services. I told you that the best option for this is Kubernetes. Auto scaling should respond to queue depth, latency, and workload demand. And GPU and LLM resources must be scheduled carefully. Bottleneck analysis help identify the real performance constraint, as we discussed in section 6.8. Predictive scaling prepare for known business workload spike. So all that we teaches in chapter 6 is how to scale multi-agent system safely, efficiently, without any bottleneck. So let's run through the sections. In section 6.1, we discuss horizontal scaling and vertical scaling. And in section 6.2, we discuss agent pool management. How do you manage agent pool and their state? In section 6.3, we looked at microservice architecture for multi-agent system, which is, of course, is Kubernetes. And in section 6.4, we have orchestration with Kubernetes, orchestrating multi-agent system with Kubernetes, how you should design if you are deploying on-prem or using any of the cloud, Azure, AWS, and Google. In section 6.5, we looked at cloud native deployment patterns. And in section 6.6, we looked at performance monitoring and profiling. 6.7, we look at bottlenecks and how to resolve bottlenecks. And 6.8, we looked at auto scaling for Kubernetes pod. So this is all we have in chapter 6. So let's run through what we have in this slide. These are just a little bit of the information we have from the book. Get the book to see the full information on each chapters from Amazon. So the problem statement here is that surviving the inevitable scalability reckoning. So what work as 10 agent processing 100 tasks will inevitably crack under enterprise grade volume. So you cannot use what work for 10 agents implementing 100 tasks to design for 10 agents that will be implementing 1,000 tasks. No, that system is going to fail. So you cannot use that design pattern. So you must design for the capacity of, based on the workflow volume. You must put that into consideration to know the number of agents you should design and how you should design for the workflow distribution. So subtle signs of limits. Limits show subtly. Procurement approval slow from 8 to 22. If you are implementing old pattern for new pattern which has increased workflow, you notice, for instance, that in procurement agent you have a approval slow from 8 to 22 because the agents are overloaded. IT queues swell from 50 to 300 because why? The IT manager agent is overloaded. So you don't know whether you should increase agent or you should increase LLM core. You see why scalability is very, very important and when to scale. Then another problem is architectural decision. So predictable consequence of single orchestrator, centralized task queue, or decentralized shared database pool. So you don't know whether it is the architecture that is failing or the architecture cannot carry what you have designed. Then design for horizontal growth. So make sure when you are designing, design for horizontal growth from day one instead of retrofitting under production pressure. So make sure you put scalability into design for horizontal or vertical scaling from day one. Throughput versus reliability. Distinguish throughput need, for example, supply chain, from reliability need, which is legal orchestration to solve the right problem. So you must distinguish needs from distinguish between throughput and reliability. So you cannot be solving throughput problem where you need to solve reliable problem. No, 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 it's a wrong approach. So know what fails, know what is failing, and know what is drawing back the system and design to resolve it. Scale up when you need to scale up, and scale horizontally when you need to scale horizontally. Okay. So in 6.1, we talked about scalability in general, where we said vertical scaling is making one virtual machine bigger, that is increasing the capacity, which is also called scale up or scale down. Then horizontal scaling, you add more instances. Instead of increasing, you add more instances, which is known as scale out or scaling. When you reduce your scaling, when you scale out, you add more. So for enterprise multi-agent system design, horizontal scaling is generally better because there is parallelism of operation, there is mass capacity surge, there is agent scale you have agent scale independently because the agent can be working independently, so they scale independently. You cannot go and be scaling agent that is doing one work based on the capacity or based on the scale that you give to agent that is doing 10 works. So you are going to be wasting money there. So stateless and stateful scaling. Stateless agents store no task specific memory between execution. So stateless does not keep memory. It does not keep information. So you can also use stateless scaling, while stateful agents keeps important memory inside itself. It makes horizontal scaling harder because state must be in sync with the system. So stateless design is better for enterprise scale design. So when you're designing for enterprise scale, you can use stateless design, which is, it allows you to scale or horizontally. But stateful is good for vertical scaling because when you state horizontally in stateful agentic design, you will lose information. The information will not be added to the new virtual machine or the new instance that you are adding. Sharding for high volume workload. Route related works to the same shared. Make sure related work are routed to the same shared. Okay, so this improve catch locality, audit grouping, state consistency, and parallelism. So risk overloading. So make sure you do not overload the agent. Scale up when you need to scale up and scale out when you need to scale out. So these are what we discussed in section 6.1. So identify the actual constraint before scaling. Make sure you identify what needs to be scaled, what the problem is, what is slowing down the system before you actually scale. So common mistakes here are adding agent instance when the bottleneck is infrastructure or algorithm. So when you have infrastructure problem, don't go and be adding more agents. When your algorithm is not right, don't go and be scaling infrastructure. You'll be spending money, in the wrong place. So scaling dimension, evidence, and recommended action. If what is causing the problem in the system is infrastructure, maybe you've got from your metric, you see that the database or the LLM weight ratio is greater than 30%, then the action you should take is expand connection pools or increase API quotas. If the problem is the database, expand the connection pools. If the problem is LLM API call, you can increase the API quotas. You can see why it is very, very important here. Agent count. If your scaling dimension is agent count, or what is causing the problem in the system is agent count, and you've gotten the evidence from your metric that there is high utilization, which is greater than 80%, plus growing queue, then the action you should take is scale out the specific agent pool type. And then we have agent capability. So a high queue depth plus low utilization. So you discovered from the metric that high queue depth plus low utilization is what is causing the problem of the capacity of the agent. The recommended action for you to take is that you switch from single threaded to async dispatches. So change from, using single threaded to asynchronous or dispatches or to event driven. So you can see why it is important to observe the system and to know what needs to be scaled. So system reliability is very, very important. And as we have said in chapter 3, you cannot monitor, so monitoring is useless when you are not using the outcome of the log, your metric, to make your multi-agent system perform better. So observability always win. Make sure you observe the system, collect utilization metric, collect growing queue metric, collect API call and database call or ratio, and make sure you collect IQ depth metrics and low utilization metrics. This allows you to know what needs to scale and what is causing the system downtime. So also in section 6.1, as I have discussed earlier, we have stateless and sharding. So statelessness and sharding, as we have said, for horizontal scaling is better for enterprise multi-agent system design because you can add more instances. And for that, for horizontal scaling, stateless is better. In stateless scaling, you do not keep information in the memory. Though information is not stored in the memory, they are automatically discarded. So the coupling state is required for elastic horizontal scaling. So stateless agent design. Agent hold no persistent state, retrieving context from Redis at execution start. So agent does not keep context within their own memory. They don't store it themselves. They are stored outside in a connected database like Redis cache, so that when you need to to scale horizontally by adding more agents, you will not be losing information. The new agent that you're adding can still draw the information from the database like Redis cache or PostgreSQL. So load balancing, another form of scaling is load balancing. Allow load balancer to distribute tasks without needing session affinity. If session affinity is needed, you will also lose sessions because the hold agent will be given the session that is not in the new the new agent. Consistent hashing and sharding. High volume workload like 50 schools use sharding for data locality and caches. Okay, implement sharding and consistent hashing as well. So use hash distribution if you are using load balancing, not round robin. Entity ID sharding. Sharding by entity ID route related tasks to one shard, reducing coordination. So this is why you should give agent pool identity. Let each agent have their own identity so that tasks can be routed based on identity instead of randomly. So this improve coordination of the coordination between the agent. We have statistical rebalancing. So use virtual node in the hash ring to mitigate hot spots on overloading shard. So these are ways that you can design for scalability in multi-agent system. Know what to scale, and for enterprise multi-agent, horizontal is better, and for horizontal, make sure informations and sessions are stored in Redis cache, no in memory. Agents should not keep session, should not keep memory within themselves. So agent pool lifecycle, this is what we discussed in section 6.2. So agent pool management and lifecycle. Agent pools must support the following, as we have stated. So the first one is initialization. The second one is scale up. Agent pool must support scaling up, that is increasing the capacity instead of adding more. The agent pool must also support scaling down. It must support draining and rolling updates. It must support earth replacement, and it must support version management and termination. So these are very, very important. So maintaining continuous availability requires sophisticated rolling updates and graceful instance draining. So when you are designing agent pool lifecycle, make sure you implement rolling updates. That is, replace instances one at a time by adding version 1.3 before draining version 1.2 to avoid downtime. So do not just remove version 1.2. Make sure you add before you remove so that there will not be downtime in the system. Then you can also implement graceful draining, which is never abruptly terminate an agent. Make it draining and wait for tasks to complete. So if there is a task that the agent is doing, let it complete the task and drain all the information in the agent before you take it down. Health replacement. Automate lifecycle triggers to replace instance failing health check without intervention. So you can, automate the life cycle of the agent instead of just abruptly replacing them. So load balancing is good here. Version pinning. Support workflow that must complete on the same version to avoid breaking changes. So let support workflow complete uh, before you change abruptly. So keeping agent version like version 1 or version 2 is very important. Then we have pool state. Track initializing, active, scaling, draining, and terminated state for transparency. Make sure you track what is happening in the agent pool. Track your initialization, track agent that is active, track scaling, how you should scale, track draining, that is when you are draining the agent of a specific session or task, track everything, and terminated states for transparency so that you will not be losing a session or information. And in the section 6.3, we discuss microservice architecture integration. So how do you integrate a multi-agent system with enterprise workflow? So integrate enterprise agent like normal microservice. When you are building microservice applications you deploy, one application does not depend on another one, and that is why we call them cloud native, and the platform designed for that is Kubernetes. So Azure Kubernetes service is there, AWS EKS, Elastic Kubernetes Service is there. GKS is there if you want to, if you're a Google Cloud fan. So production grade agent service, encapsulating agent capability with standardized API contracts, enable independent scaling and deployment. So here you should design for container isolation. Each agent type run in its own container with separate resources and a uniform API. So if you are using Kubernetes, then each agent will have its own pod. So you can track the task done by the agent, the health of the agent, and the metric output of the agent. So you know what is happening to a particular agent. Then also, you can also use a liveness or readiness design. Kubernetes using health to restart, failing containers, and ready to stop traffic to agents that are busy or warming up. So, of course, Kubernetes is good at handling distributed system and microservice architecture. So it is basically designed for that. So integrate enterprise agent like normal microservice, as we have said. Each agent must have its own container image in what we have in part 1 here. Each agent must have its own deployment. Each agent must have its own health check. Each agent must have its own scaling policy, must have its own metric and API constructs. That's what we have said. Then service mesh, just like we have data mesh, where you build data as a product instead of one siloed warehouse. You design product. So designing data product is building tables or relational or star schema tables based on business unit instead of just having one single source of truth for the whole enterprise. You break them down into agentic mesh as well. So this agentic system design, as I told you before, draws from software engineering and data engineering. It's combined the whole operation together. We have agentic mesh as well. I don't know if you have read the book from O'Reilly, agentic mesh. So build agents as surface mesh. Okay, do not combine procurement agents with supply chain agents. Do not combine supply chain agent with IT operation agents. Do not combine IT operation agent with finance agent. Do not combine finance agent with legal agent. So make sure there's separation. Okay, build agent as one single pool or implement agentic mesh. So use Istio for traffic management, align priority-based routing, e.g. routing critical task to a premium or pool. So agent distribution, agent uses a microservice architecture as well. Multi-agent system uses microservice architecture. Each agent should expose a uniform microservice API, uniform service contract, makes orchestration monitorable and scalable. It makes scalability and monitoring easier. So make a uniform service contract makes orchestration to be easy to monitor and easy to scale. And just as we have said, implement service mesh. This help avoid implementing all of traffic routing, mutual TLS, retries, timeout, circuit breaking, outlier detection, traffic splitting, and observability in one. So when you implement surface mesh or agentic mesh, you have separate infrastructure for separate agents, and this improves reliability concerns. This solves the problem of reliability concern from agent logic. So implement agent as surface mesh, build agentic mesh instead of building one platform of swarm agent for the whole enterprise. So implement them as mesh. Let each department or each business unit have their own agent pool. The circuit breaking automatically stops sending requests to agent pool that are failing, giving them 60 plus seconds to recover from outages. So implement circuit breaking in your design pattern. Then it also implement agent card pattern, so which is where you use the capability endpoint to advertise supported task types, input schemas, and output requirements. So these are very, very important in multi-agent system design. Orchestration with Kubernetes. So of course, when you talk of microservice and distributed system, the best platform to deploy that is Kubernetes, because it is built natively for microservice application. So also treat multi-agent system as microservice, deploy them as microservice architecture. And the platform that is best for multi-agent system is Kubernetes. You can't debate that. Leveraging cloud native primitive to manage containerized agent fleets at massive scale. So deployment, statefulness, horizontal pod, or autoscaler can be fully implemented there. Here, cron jobs, rolling updates, pod distribution budget, health proofs, topology spreading are all the design pattern that must be implemented here. We have agent deployment manifest instead of Kubernetes manifest. So Kubernetes deployment must protect in-flight tasks and maintain availability during upgrade or node maintenance. Horizontal pod also autoscaler uses queue depth, urgent utilization to scale up or down. And then we have scheduled scaling for predictable demand. So when you have predictable demand, you can implement scheduled scaling. Okay, so where you have some workflow, some workload are predictable, some workload are reactive, and you have reactive scaling that may be too late. So you should implement schedule scaling for such a task. So these are the sign pattern that you should implement. So leveraging cloud native primitive to manage containerized agent fleet at massive scale. For deployment, your deployment strategy should be to use mass search and mass unavailable settings to ensure 100% availability during agent version upgrade. So before you upgrade the agent version, make sure you use mass search and mass unavailable. Then resource. So resource management, you can set your CPU/memory to request for guaranteed allocation and limit for burstable ceiling of 2 times typical usage. And then we have pod distribution budget. So enforce minimum availability. That is, use the function minimum mean available equals to 2, etc. to prevent cluster maintenance from taking down critical posts. Also, you can also, that is for pod. Then for CADA, uh, so for CADA, you can schedule scaling, use cron triggers as we have studied to pre-scale pools before known surges such as Monday morning procurement batches, etc. And then for topology, topology thread. So topology, of course, from mathematics, you know, topology has to do with continuity. So force pod to spread across different hosts. So talking about the continuity and the area, the networking of the agent. So make sure you force pod to spread across different host nodes to prevent a single hardware failure from taking down an entire agent type. So we have 6.5 where we discuss cloud native deployment patterns. So balancing GPU efficiency and deployment pattern, we have dynamic allocation makes agent workload economically viable. So for cloud native deployment pattern, depends on workload. This depends on workload type and cloud, the type of cloud that you are using. So you know, cloud is elastic, it is managed, and it has variable costs. Okay, so dynamic allocation make agent workload economically viable. So you have many choices for GPU efficiency and deployment pattern. You can use cloud, you can use on-premise, you can use hybrid, that is keeping some on cloud and some on-premise, or you can even use multi-cloud or deployment. So hybrid, for on-premise, you have fixed cost, You have full control of the whole infrastructure, and you have data sovereignty. Your data lives on your system. It lives inside your organization. Then for hybrid, where you have cloud and on-premise combined together, so you can have some agent-based deployed on-premise, and you can have some burst into cloud when they need scaling. And then you can also implement multi-cloud by deploying to multiple cloud and linking them together using Azure Arc. So multi-cloud provider, AWS, Azure, and GCP can be also used for deployment. We have pattern by workload. So regulatory constraints, data sovereignty, and requirement matter more than cost. Okay, so it's not every time that you should, be focused on cost. You have to, implement trade-off. So what matters and why does it matter? Okay, so regulatory constraint is important. Data sovereignty, for example, in Nigeria, CBN just issued, a law enforcement that in every financial sector, transactional information should not be taken across border. That is, everything should live within the system in Nigeria and should not be stored in other country or in other region. Okay, so you can see that. So for that kind of operation now, you cannot use cloud. If you want to use cloud, you can keep transactional information in your on-premise data center, and then the information that are not transactional that can cross border can be kept in other Azure region if you are using a cloud in other data center outside Nigeria on Azure. So we have GPU pattern. So dynamic agents should request GPU only when needed. So do not let agent request CPU every time. They should request CPU only when it is needed, so that you will not be running unnecessary costs. And you know that GPUs are very, very expensive. So these are the kind of design pattern that you can implement: fully on-premise or hybrid on-premise and cloud for burst stable workload. You can implement one cloud, or you can implement multi-cloud. You can choose pattern based on workload. Okay, does your data need to be sovereign? Are you keeping data that should not be kept in other region? Do you want to design for data that should not cross border? So you should put them into design. So cost is not what you should consider here. Where you should consider cost is GPU scaling or scheduling. So we have pattern choice. Yes, choose cloud for high variability, and on-premise for data sovereignty and sub 50-second latency. So implement hybrid bursting. Hybrid bursting, maintain a fixed on-premise base capacity and burst to cloud for predictable peaks. And GPU scheduling, move away from one GPU per agent to a shared pool model where agent request GPU time only for inference call. So they only request GPU when they are making inference call, when they are implementing a large task that require higher token or higher API call. So you should also put this into your design. Then utilization ROI is a return on investment. So on-premise GPU infrastructure needs approximately 70% utilization to justify cost. So dynamic scheduling maximizes fleet wide. And then we have a priority queue. So priority queue is where you implement a GPU scheduler that prioritizes real-time IT classification over latency tolerance and rigorous fields. So these are the design patterns that you can put into consideration as you design for, or as you consider cloud native deployment patterns, or whether you want to implement hybrid or fully on-premise. And then we have section 6.6, where we discuss performance monitoring and profiling, so which is observability. So observability is very, very important in multi-agent system orchestration. So achieving deep observability across spans. Traditional metrics are insufficient here. You can't keep normal metric like your SLO, SLI, and error rates. So we must trace. You must implement trace. All the agent workflow activity must be traceable. Okay, in the entire journey from orchestration to execution, everything must be traceable. So, and these are the things that you should measure. Number one is task duration. Number two is queue depth. Number three is LLM inference time. Number four is LLM token usage. Number five is tool call latency. Number six is tool call failure rates. All these must be measured. Okay. And number seven, we have agent utilization, which agent is used most and which one is not used at all. And then number eight, we have distributed traces. The agent traces, their path must be closely monitored. Those metrics must be collected as well. So observability connects the following together. It connects cost, latency, error, queues, and traces all together into your report, so you know the problem that is happening in the system, and then you can design for correction to make the system reliable. So we have agent span arc. So traces flow from root span through orchestration, task execution, and tool call. We have queue depth gauge. As we have said, this is how it works. Fill queue depth by priority to identify missed SLAs before production impact. And then tool success rate is monitor tool failure rate, a 5% fail rate, impact overall task success. And then also implement bottleneck analysis, where trace time spent on LLM inference versus waiting for external ERP responses are measured. And then collect critical metrics like track task completion ratio and LLM token velocity to detect loops in the system. And then we go to section 6.7, where we discuss bottlenecks, performance bottlenecks. So bottleneck detection should use evidence, not intuition. So you cannot just design for institution in multi-agent system. No, you must keep facts. So when you have facts, you can act on the facts, because when you are not collecting facts, when you are designing based on assumption, assumption cannot work. Intuition cannot keep agent scalable or reliable or improve performance. No, you must design for bottleneck detection so that you have evidence of whether you should scale the system, or whether you should implement load balancing, or whether you should add agents, or whether you should increase uh, LLM API call and so forth. So we have predictive elasticity. So move beyond reactive scaling to preemptively manage load based on historical enterprise pattern. So as we have said, do not use intuition or assumption to design for bottleneck. Use evidence of what is happening in the system, and this is why observability and metric collection is very, very important. So reactive scaling, scale based on CPU, that e.g. CPU is greater than 70%, or queue depth to manage unexpected spikes. So when you have reactive scaling, you can scale based on CPU or queue depth. Economic scaling, when you are considering cost management, then you can use off-peak spot pricing to process background batch workload cheaply. And then for predictive scaling, you can use historical data to prescale for batch load, avoiding latency. Then the golden rule here is scalability relies on early decision on stateless and infrastructure. And then in conclusion, all through here in this section, all we discuss in the book is diagnose first. Make sure you observe the system, diagnose first. Do not add agent if the LLM API or algorithm is the bottleneck. Okay, so make sure you design for bottleneck and solve the problem. And then lastly, in the last section, Okay, in the last section we discussed auto scaling in general, so which is not on this side, but adjust capacity automatically. In auto scaling, you can design your Kubernetes to auto scale where the capacity is adjusted automatically. That will be scale up. So good auto scaling combine predictive scaling, reactive scaling, economic scaling all together. So that is good auto scaling. It take note of predictive, reactive, and economic, so that you will not be losing in one aspect. There will be cost of optimization, reliability, and the scalability all at the same time. And what that will give you is, performance, uh, efficiency. So then we have predictive scaling. We have that predictive scaling reduces latency spike because capacity is ready before demand arrives. So all that is all we discuss here. And of course, how you should read each chapter is that scalability and performance engineering for architecture for enterprise mass. So that is what we discussed there. Everything is scalability and performance engineering for enterprise multi-agent system design. So guys, let's look at the visualization in this architecture that I attach here. So we have scalability and performance engineering, designing multi-agent system for enterprise scale operation. So the stage one of the architecture for scalability and performance is ingress layer. So determine the ingress layer. How often, what is the speed at which data, as which information of workflow rushes into the system. So here you use you have your user slash event, you have API gateway, you have workflow ingress, all linked to the orchestrator engine. Then you have stage two, which is core execution layer. You have your task route and sharding from orchestrator to agent pool. So you have agent pool A, which can consist of several agents. Agent pool B, also a combination of several agents. You have agent pool C, also a combination. We have agent pool D. You can see the reason why you should design agent based on business units. So this is business unit A agent, business unit B agent, business unit C agent, business unit D agent, so that all the agents are not just combined into one single architecture. So you can design, observability for each of the pool and then collect metric from each of the pool and, measure the metric differently. Then we have stage three, supporting infrastructure layer. So the supporting infrastructure for the Kubernetes orchestration can be, so this will be deployed on Kubernetes. We have the orchestrator engine on its own pod. We have the agent pools on their own pod as well. And then we have supporting infrastructure layer. You have message broker for like Rabbit MQ. You have Azure Service Bus for this kind of operation. You have caching. You can use Azure Redis cache. You have a state store. You can use Azure SQL database or Azure SQL database for Postgres, or even Azure DynamoDB. Then we have vector database. You can use Azure Search for this, or you chunk and embed the information in a vector database. And then we have external APIs. So external APIs connection. So you can also connect to external APIs and LLM slash GPU pool. Then we have stage four, which is monitoring and scaling the pool. So stage four is where you know what to scale based on your observability or log reports. So here you've collected the right metric as we discussed in the slide. You've collected the queue depth metric, the auto-scaling metric, and the predictive and reactive and economic scaling metric. You have all the metric. Then based on this metric, you can determine the bottleneck analysis. Okay, you can determine what the problem is and how you should solve the problem. You understand? So you can determine whether to implement latency, to increase latency, or to increase rate limit, or to increase the GPU capacity, or to, or implement human queue or use human in the loop. So these metrics and logs allow you to, determine the bottleneck and solve the problem. So all this put together enables you can implement horizontal scaling or vertical scaling depending. You can have it enables better throughput. You have better throughput and seamless agent operation. You have resource efficiency, and you have a performance feasibility in the entire workflow. So scaling principles, 3-point key takeaway. So number one, keep agent as stateless as possible. So you can implement horizontal scaling, for which we said is particularly good for enterprise use cases. Then scale the true bottleneck. Don't go and be scaling wrong bottleneck. Don't increase latency where you should increase rate limit. Do not increase rate limit where you should increase GPU capacity. Do not add human in the loop where you should, add agent itself. You understand? And then key number 3, combine reactive plus predictive. Do not just design for reactive while leaving predictive out. No, combine reactive, predictive, and economic scaling all together in your multi-agent system design. So this is the end of all we have in chapter 6. We have the full information, the design pattern in diagram and code in the book. Do well to get the book on Amazon and implement those design pattern in your multi-agent system. Okay, and